P4, we're going to talk about graphs of equations. In example 1, we're going to determine solution points. So we want to determine whether each point is on the graph. So we're going to take our point, plug the first number into x, the second number into y, and see if it makes sense as a solution. So we have 13 is equal to 10 times 2 minus 7. 13 is equal to 20 minus 7, so 13 equals 13. So this is true, so yes, this is a solution. For B, we do the same thing. We're going to plug in -1 into x and -3 into y. So -3 is equal to 10 times -1 minus 7. So -3 is equal to -10 minus 7. -3 equals -17. This is not true, so no, this is not a solution. There's a couple different ways that we can graph. One is the point plotting method. So sometimes when it's an equation we know, like y equals mx plus b, it's clear that we know b is our y-intercept, m is our slope, and we can graph. Sometimes when it's a funky equation or a funky function, we may want to plug in points to figure out how our graph looks. So you can always plug in values for x, get values for y, or f of x, and that'd give you your point x comma y, or x comma f of x. F of x is just a fancy way of saying y. These mean the same thing. So in example 2, you can make a table and plug in points to graph, or we can see that we have a linear equation here. This is almost in y equals mx plus b form, so we can just rearrange the right side. We're not moving it to the other side, so we don't change the sign. So y equals -3x plus 7. So 7 is our y-intercept. We'll call it b, or y-intercept. -3 is our slope. So we can call it -3 over 1. So we're going to start by plotting our y-intercept. So we're going to go put a point at 7 on the y-axis. Then we have the slope of -3 over 1. We can call this rise over run. We're going to go down to -3 and to the right one. Down -3 and to the right one. So this would be our line. Be careful when you're putting this slope that you're going in the correct direction. If you have a negative slope, your line should be decreasing. Next, we're going to talk about intercepts. So intercepts are where the graph intersects or touches the x or y axis. So we're going to have x or y intercepts. So on the next page, if it crosses the y-axis, it's a y-intercept. It could have one y-intercept. Could have, here we have 3 x-intercepts. Here we've got 2 y-intercepts, 1 x-intercept, and then in the circle we have no intercepts. It doesn't touch, and it will never touch one of the axes. So to find the x-intercepts, we let y equal 0. So we plug 0 into y, and we solve the equation for x. To find the y-intercepts, we let x equal 0, and we solve the equation for y. In example 3, we're going to find the x and y-intercepts of the graph. So starting with the x-intercept, for our x-intercept, we want to plug in 0 into the y. So we have 0 is equal to x cubed minus 4x. Here you can solve however you want. We see that we have multiple x's in our terms, so we know that we have to take out the GCF since that is in common. So I'm going to take out an x. We're left with x squared minus 4. X squared minus 4 can be factored more, so this is x plus 2, x minus 2. Then we can just set each piece equal to 0. So x is equal to 0, x is equal to -2, and x is equal to +2. We want to write them as x-intercepts. So the x goes into the x spot in our point, and 0 we plugged in for y, so we're going to put 0 in the y spot. So 0, 0. Next we have -2, 0, and +2, 0. So these are x-intercepts. Next we're going to find the y-intercepts. So to find the y-intercepts, we plug in 0 into the x's. So we have y is equal to 0 cubed minus 4 times 0. So y is equal to 0. So here our y-intercept, we put the y-intercept into the y spot, 0 we plugged into the x, so 0 goes into the x spot, so 0, 0. So these would be our y-intercepts. Next, we're going to talk about symmetry. So graphs of equations can have symmetry with respect to one of the coordinate axes or with respect to the origin. Symmetry with respect to the x-axis means that if the graph was folded along the x-axis, the portion of the graph above the x-axis would be the same as the portion below. So if I had a graph here, and if we had symmetry along the x-axis, if my graph went this way above the x-axis, it would have the same shape below the x-axis. So that x-axis acts as the mirror when we have symmetry along the x-axis. So we could have symmetry along the x-axis, the y-axis, or the origin. So here's an example of each. In the first one, we have symmetry along the x-axis. So if you fold the graph over along the x-axis, we have the same shape. Notice how here in our points, the x's stay the same, but the y goes from being positive y to negative y. When we have symmetry in the y-axis, our graph is symmetrical along the y-axis. The y's stay the same, the x's change signs. So we would have a point on our graph at, we could call this 4, 5, and then the other point would be negative 4, 5. And this would be symmetrical about the y-axis. Symmetry around the origin is a little bit different. We can't just fold our graph to get the same picture, but if we have x, y as one of our coordinates on our graph, we're also going to have negative x, negative y on our graph. So if I had a point here that was 3, 6, then this point here, negative 3, negative 6 would also be on our graph if it was symmetrical about the origin. So symmetry helps when we're graphing. It says knowing the symmetry of a graph before attempting to sketch it is helpful because then you only need half as many solution points to sketch the graph. If I knew that my graph was symmetrical about the x-axis and I had points over here, then I know it's going to have the same points over there. It's helpful when graphing parabolas. We know that we have an axis of symmetry not on the x-axis, but it could be anywhere. It could be on the x-axis. But wherever the axis of symmetry is, if our graph went like this on the left side of our axis of symmetry, the other half is going to go like that. So with parabolas, we use the axis of symmetry to help us graph. So graph is symmetrical with respect to the x-axis whenever x comma y is on the graph, and also x comma negative y is on the graph. So if it's symmetric on the x-axis, the x's stay the same, the y's are what change signs. If it's symmetric around the y-axis, the y's are going to stay the same. So x comma y is on our graph, so is negative x comma y. And a graph that's symmetric with respect to the origin, if we have x, y on our graph, then so is negative x, negative y. So it says you can conclude that the graph of x squared minus 2 is symmetric with respect to the y-axis because the point negative x, y is also on the graph. So when the y stays the same and it's the y-axis, the x is what changes. So notice here, not only is the y-axis acting as a mirror, but also the y's stay the same, the x's are what change signs. So this is symmetric along the y-axis. We can test for symmetry algebraically. So it says the graph of an equation is symmetric with respect to the x-axis if replacing y with negative y yields an equivalent equation. So if we plug in negative y into y and get the same equation, then it would be symmetric over the x-axis. Same thing if we plug in x with negative x and end up with an equivalent equation, so the same thing, then it would be symmetric over the y-axis. And then if we plug in negative x and negative y and get an equivalent equation, to the original equation, then it is symmetric over the origin. So in example 4, we're going to test for symmetry. So we want to, it doesn't really matter what we try first. We can test for symmetry on the y-axis. So when we test for symmetry on the y-axis, we're going to plug in negative x. So y is equal to 2 times negative x to the third power. When we simplify this, we get y is equal to negative x to the third power would be negative x to the third power. So we can call it negative 2x to the third power. This is a different equation than this, so it's not symmetrical on the y-axis. Next, let's test on the x-axis. If we're testing for symmetry on the x-axis, we're going to plug in negative y. So negative y is equal to 2 times x to the third power. This is a different equation than this, so we're not symmetrical on the x-axis. Now let's test on the origin. So we're going to plug in negative x and negative y. So negative y is equal to 2 times negative x cubed. When we cube the negative x, the negative, it stays negative, so the negative can go to the outside. So we have y, negative y is equal to negative 2x cubed. We can simplify by dividing both by negative 1. We get y is equal to 2x cubed, which is the same thing as the original equation. So it is symmetrical about the origin. One way that's helpful when you're testing for symmetry is if you know the shapes of the graphs. So an x cubed graph looks like this, which is not symmetrical about the x-axis, not symmetrical about the y. So then it helps to only have to test the origin. Last thing we're going to talk about is equations of a circle. So our circle formula comes from the distance formula because we have the center, which is hk, so that's our h and k. We'll have a point on the circle, which is an x and y, so any point on the circle. And then our radius is the distance from the center to the point on the circle, so that gives us r. So it's saying the radius is equal to the distance formula. We're finding the distance from the center to the point on the circle. So our circle formula is x minus h squared plus y minus k squared is equal to r squared. Don't forget that the r is squared. So our h and k comes from our center. We always change the signs when we plug them in because it's x minus or y minus. So our circle formula is here again on the next page. It says the radius is r, the point xy lies on the circle, and h and k is the center. So don't forget h and k is your specific center point. The formula down at the bottom here is when h and k is 0. So when we have a center at the origin, because then we wouldn't have x minus h squared, it'd just be x squared. So that's why we have the separate formula here. But if you plugged in 0, it would simplify to this. In example 5, it says the point 3, 4 lies on the circle whose center is at negative 1, 2. The center is our h and k. A point on the circle can be our x and y, and we have to find the radius. So we want to find the distance between the center and the point on the circle. So we can use our distance formula. So we have the square root of x2 minus x1. So I'll label this as x1, y1, x2, and y2. So negative 1 minus 3 squared plus y2 minus y1, which would be 2 minus 4 squared. So negative 4 squared plus negative 2 squared would be 16 plus 4, so we have the square root of 20. Typically, if I was just giving my answer as the distance, I'd want to simplify this, but because we're plugging it into the formula, I'm not going to simplify it, and you'll see why in a second. So we're going to plug it into our circle formula. So our circle formula is x minus h squared plus y minus k squared is equal to r squared. So because it's equal to r squared, we're going to end up squaring this because this is just r. So when we plug in our h and k, we have x minus -1, so it turns into x plus 1 squared, plus y minus k would be y minus 2. Our k was 2, so we're using our center here, squared, is equal to r squared. So we'd square both sides of our radius, so the square root ends up canceling out, so it's equal to 20. So that would be our equation of the circle, the standard form of the equation of a circle. The one other question that you may see with equations of a circle is if it gives you two endpoints on the circle that go through the center, you want to find the midpoint of the two endpoints. So if it gives you two endpoints, you want to find the midpoint, then that would be your h and k. Then you can find the radius. So there's an extra step if it only gives you two endpoints. So make sure you read the question and see what it's asking, because there's a couple on WebAssign like that. Application just talks about different ways that you can solve problems. You can construct a table. With the numerical approach, with the graphical approach, you can draw a graph, and then algebraic, you can use the rules of algebra. This doesn't really apply. And we're just going to skip the next one. It's just stuff we'd plug into the calculator. But there's no questions like this on the WebAssign. We can talk about it when I get back. So don't forget to turn in the notes and continue working on the WebAssign.